Good morning everyone. Today I will present my work on sampling strategies for stepped frequency range estimation using compressed sensing. The first word you should notice is sampling strategies. Those are the rules used to choose which frequency steps are measured from the full stepped frequency sweep. This is done with the idea to reduce the amount of measurements while still keeping enough information to recover the target ranges. Next we have step frequency. A step frequency radar is useful because it can create a large effective bandwidth using a sequence of narrow band measurement. Lastly, we have compressed sensing. This is a very important technique that allows us to recover a sparse range profile from fewer frequency measurements than normally required. But one thing we should notice, the range profile should be sparse. In practice, this is very often the case because a radar takes quite a lot of measurements and there are not that many targets in the range profile. Alright, the main question we try to answer with this report is, can we reduce the number of measured frequencies without losing the important range information? This is a highly relevant question and very important because very often is the scenes moving while you are still measuring. And this can be a big problem when the measurements takes too long. Before you calculate where the object is, it's already moved. Your measurement is no longer relevant. So the measurement should be taken quickly and should be done with a light algorithm and a very smart sampling strategy. Okay, I've mentioned earlier quite briefly what stepped frequency radar is. I will not go into more details. Stepped frequency radars transmit pulses at different carrier frequencies, and each pulse gives one frequency domain sample of the scene. By combining all the frequency samples, the radar synthesizes a wide bandwidth. This wide bandwidth is what allows fine range resolution. Alright, the radar sends a frequency to the transmitter channel and will receive it in the receiving channel. And what he received is of course with the delay. But these delays can be recovered with an inverse Fourier transform, and eventually doing some calculation using the formula tau is 2 times the distance divided by the rate of speed, we can determine what the distance is of the target. I mentioned before that we can recover it through the inverse discrete Fourier transform. However, in theory you will get only a delta spike, but this assumes an infinite bandwidth. In practice, it's impossible. There's always a finite amount of bandwidth, so we'll get a sinc function, which is dependent on the height of the bandwidth. There's a trade-off in the radar design, because sending too many frequencies take too much time and also too much computation power, which cannot be used in high moving scenes, as I've mentioned to the motivation. So the range resolution depends on the bandwidth through this formula. And as bigger the bandwidth gets, the more it acts like a delta function. And there are multiple ways of decreasing the amount of steps we're measuring. The first is very simple. We just take the half of the amount of frequencies and we use that. The problem is our bandwidth will increase in 2 times and it's hard to distinguish between the used target. Another sampling strategy is to just double the step size, but that will create range ambiguity, meaning we'll get multiple ghost peaks, which could be a possible target location. So now we cannot say with certainty where the target is, and it's also not ideal. This is where compressed sensing enters. The full range profile is written as vector x, and in our case is known beforehand that x only consists of 4 non-zero entries, so as you can see x is clearly sparse. And we want to use, instead of all n frequencies, like I've said before, we have a step frequency response, it will set n frequencies, we only want to use m, and m is smaller than n, and I denotes the used m frequencies. Alright, and omega will tell you which of the frequencies, give you the index of the selected frequencies. Okay, and here we have a omega, and this is the sensing matrix. with only the rows that correspond to those selected frequencies. This will give us fewer measurements than unknowns. Ideally, we would recover the sparsest range profile, meaning the X with the smallest number of non-zero entries. However, directly minimizing the number of non-zero entries is NP hard. So in practice, we use an approximation method, and in this project, this method is OMP. First, OMP correlates the current residual with every possible range bin. So in simple terms, it checks which range bins best explains the part of the measurement that still explains. Secondly, it will pick the strongest bin. The bin is added as a detected peak. In my implementation, a new peak must be at least 30 centimeters away from the already chosen peaks. This is done because we have knowledge about the setting, and is also done to prevent that one broad reflector will result in multiple selected peaks. Okay, after that, OMP will refit all selected peaks together using least squares. This is important because once a new peak is added, the amplitude of the previous peaks may need to change. It may change. So afterwards we will subtract the fitted signals from the measurement, and what remains is the new residual, which can once again correlate. But in our case, this process is repeated only 4 times because we know that the sparsity is 4. However, in many practical applications, we do not know the sparsity before, and we have to do this until a stopping criteria, which I will not cover right now because it's not relevant for our situation. The equation that you can see here defines the mutual coherence. After we choose a subset of frequencies, each possible range bin has its own response in the reduced sensing matrix A alpha. The vectors AI and AJ represents 2 possible range bins. Mutual coherence looks at the largest normalized overlap between any of these large responses. So this is the correlation term, and this is the normalization term. In our case, it's Fourier transform, so we don't really need to normalize, but I'll leave it here as a formality. And we want the maximum. So mutual coherence looks at the largest normalized overlap between any 2 of these responses. So low coherence is good, because different ranges look different. High coherence is bad, because one range can look like another, which can create side lobes and make OMP pick the wrong peak. The second equation shows the ideal goal, which is choose the M frequency sample that makes the worst case overlap as small as possible. This is once again an NP hard problem, so that's why it's important to have a good sampling strategy. I compare 4 sampling strategies. The first one is periodic sampling. As mentioned before, this will decrease the range ambiguity, causes multiple peaks. Like one target can create multiple peaks, so you can not distinguish where the target is exactly because there are multiple possible locations. Secondly, we have random sampling that doesn't have the problem of creating lobes. However, when we have a bad run with random sampling, we might have clustering. So we will not effectively use the full bandwidth. Instead, all points will become together and we have a high resolution instead of a low one, which we want. Thirdly, we have jittered sampling. This makes sure we cover the full bandwidth by dividing the bandwidth in blocks, and in each block we will put 1 frequency. Lastly, we have adaptive sampling. First, we will send a low amount of frequencies, and based on this information we will determine which frequencies to send and how much. So we get like an estimate where the peaks are approximately, and afterwards we send more frequencies to determine exactly, and it's also a good way to lessen the amount of measurements sent. The setup can be found here. As can be seen, the radar is mounted against the box and it will send a step frequency. This step frequency consists out of 150 different frequencies sent to the 5 items, which can be seen here. Despite that there are 5 items, only 4 peaks are detected. This can be very easily explained by the fact that the 2 deodorant bottles has approximately the same range from the radar. Another interesting thing to see is that because the tin is so broad, and the distance of course different from this angle to that angle, that you will have a very broad peak in the range profile. Alright, now we're going to the results. What you can see here is the mean mutual coherence versus the amount of measurements, and the mean is taking out 300 trials. A general trend is when the amount of measurements increases, the mutual coherence decreases as expected. Another thing to see is that random is generally speaking always lower than the other two sampling methods. And another interesting fact is that jitter is always lower than adaptive. However, during the 128 measurements, jitter breaks and is higher than the two other methods. When looking at the sampling point spread functions at m is 128, so m is 128, so there are 20 omissions. But random, this happens random, as the name says, it happens random. And for jitter, this causes near periodic, so we have the artifact of side lobes, and we have one big side lobe at 0.47 meters. Remember this, they will become very relevant later on. And for adaptive one is also quite damped. Alright, almost all methods performs really well to detect at least two targets. However, for 3, all of the methods struggles a bit. But what's the most interesting thing what we found is that jitters fail to recover 4 at 128 measurements. Why is that? When we look at the per target detection, a thing we can see is that jitter always fails to find the first one. Well, it does pretty well at finding the last peaks. This can be easily explained by the side lobe created at 0.47 meters. So the reason why jitter finds some target more than others is all done of the periodic sampling and the side lobe that's created. So we cannot only tell by the mutual coherence whether it will detect an item, yes or no. It's also important the location. And when we introduce structured side lobes, this could become a big problem when it is at a location of interest, which is happening now. Okay, well, look at the result. Does this mean that random is always the best method? We should keep in consideration we are now only considered a finite grid, while when doing live sampling, this is of course not the case. We have a uniform grid. It can be very many frequencies to choose from. Another thing to notice is that we only had 150 measurements, which is quite low. It's quite low. So I would suggest in the near future to do an experiment where we have way less measurements than when we use way less measurement than what we have measured in total, and this can be done by a 3-day variant of this experiment. And I would expect that in a 3-day variant that jitter would perform slightly better because the chance of creating side lobe at a point of interest is lower, while we are recovering the full range, recovering the full bandwidth. Another experiment we can do is in the online scene, because now adaptive did not gain much extra information from choosing a new frequency. The scene was static, and there was also not much possibility to switch. So I think in the online scene we could learn way more from the adaptive method. So to conclude, random is in our case with a finite grid and small amount of measurement is better, but we cannot conclude anything outside of our tested environment. Thank you very much for your attention. It was a pleasure giving this presentation.